Welcome to this explainer, where we're diving into one of the absolute most fascinating topics in modern tech: how computers actually learn to see. Today, we're demystifying convolutional neural networks, or CNNs. If you've ever wondered how your smartphone instantly recognizes your face, or how a self-driving car spots a stop sign from 100 yards away, well, you are in the right place. We're going to break down the exact mechanics behind this incredible technology, step by step, and really get into the nuts and bolts of how it all comes together.
Okay, so let's start with a massive question. How in the world can lines of code, which, let's be honest, essentially only understand math and logic, look at a chaotic grid of pixels and confidently know it's looking at an apple? We're going to answer this exact question today by tracking a digital image of an apple as it moves through a sort of computational assembly line. It's this wild journey from raw visual data to a highly confident prediction, and it all relies on a very specific type of architecture.
And that architecture is what we call a convolutional neural network. At its core, a CNN is a highly specialized deep learning algorithm. Now, standard neural networks are great for a lot of things for sure, but they easily get totally overwhelmed by the sheer complexity of high-resolution images. Enter the CNN. It's designed specifically to extract, filter, and recognize visual features before ever trying to make a final judgment. To really understand how this works, we're going to trace an image through a 5-step pipeline, starting with what a CNN actually is, then translating image channels, exploring convolution and filters, compressing data with pooling layers, and finally, flattening the whole thing for our final prediction. So, let's kick things off with step 1, understanding the assembly line of computer vision. You can really think of a CNN as a sequence of transformational stages. An image comes in at the start, gets filtered and mathematically squished down, gets lined up perfectly, and is finally evaluated at the very end. Every single step in this process is absolutely vital for taking an overwhelming amount of visual data and reducing it into a clean, readable format that a machine can actually make sense of. Moving right along to image channels, because before we can do any fancy machine learning, we first have to translate our visual apple into pure numbers. A computer doesn't see a shiny red skin or a little green leaf, right? It just sees a massive block of data. Think about the difference between a black and white image and a colored one. If we have a simple black and white photo, it's represented as a flat, two-dimensional array. We measure its length and its width. But our real world is in full color. So for a colored image of the exact same size, the computer uses a three-dimensional array. It literally takes the image and splits it into 3 distinct color channels, one for red, one for green, and one for blue. So what's actually inside those channels? Well, each pixel within them is simply mapped to a number ranging between 0, representing pure white, and 255, representing pure black. Every single pixel in our image of an apple gets assigned a specific number for its red value, its green value, and its blue value. That specific combination gives us the exact color of that tiny dot on the screen. This massive grid of numbers, spanning across those 3 layers, is the starting point of our entire network. Okay, getting into convolution and filters. We've got our massive grid of numbers representing the apple, but how do we pull out the important stuff? How do we find the curved edges of the fruit or the sharp point of its stem from all that raw data? This is where the magic happens. We use a filter, sometimes called a kernel. A filter is essentially a smaller grid of numbers that represents a very specific visual feature we want to find, like a horizontal line or a sharp curve. Mathematically speaking, convolution is just an operation where one function modifies the shape of another. But practically, think of it like using a magnifying glass to scan a giant map. The filter physically slides over our massive input array of image pixels, hunting for its specific feature. And the output of that sliding filter is a brand new array, which we call a feature map. As the filter slides across the red, green, and blue channels, it calculates the mathematical correlation between itself and the image pixels it's currently hovering over. The resulting feature map highlights exactly where the filter's specific features exist in the original image. So if we used an edge detector filter, our new feature map would look kind of like a pencil sketch of our apple, stripping away all the color and leaving just the prominent borders. But here's the catch. Sweeping a filter across every single pixel one by one creates a ton of data. To keep things manageable, we use a technique called striding. Instead of moving the filter just one tiny column to the right, we can increase our stride, moving it 2 or more steps at a time across the array. By skipping over pixels in a controlled way, we drastically reduce the size of our feature map while still keeping the general visual shapes intact. On the flip side, sometimes we actually have the opposite problem. You see, when a filter slides over an image, the pixels right in the center get scanned multiple times, but the poor pixels out on the very corners might only get touched once. Plus, the feature map naturally shrinks with every convolution. If we want to retain the original input size and give those corner pixels a fair shake, we use something called padding. We literally wrap the original input array in extra outer layers of zeros. This creates a buffer, ensuring the filter can sweep all the way to the true edge of the image without shrinking the final output.
All right, moving into pooling layers. Even after convolution and striding, if we have hundreds of different filters looking for hundreds of different features, our feature maps are still completely massive. We need a way to compress things down even more. And that is exactly where pooling comes in. Pooling, which you might also hear called subsampling, drastically compresses the dimensions of our feature maps. Imagine taking a 2x2 square of 4 pixels on our feature map and summarizing them down into just one single pixel. That reduces the size of the data by 75% in one go, all while preserving the most important features we just extracted. It's a real game changer for computational efficiency.
We can summarize these cell groups in a few specific ways, by extracting the maximum value, the minimum value, or just finding the average. The most common by far is max pooling. If our 2x2 grid has 4 numbers, max pooling simply grabs the highest number and throws the rest away. It essentially tells the network, hey, the most prominent feature in this little area is right here. This process is applied to every single feature map, tightly compressing the data into a dense, summarized package. Now we reach the final stage of our assembly line, flattening and full connection. We've scanned, filtered, and compressed our apple, and it is finally time to see how the computer actually identifies it.
At this point, we need a bridge between our convolutional steps and traditional machine learning. Our process data is currently a 3D stock of tiny feature maps, but standard fully connected neural networks, they need data to be in a single straight line. So we apply a step literally called flattening. We take our 3D blocks and just unfold them into a single-dimensional vector, a long list of numbers. This flattened output contains all the rich filtered data, but now it's formatted perfectly for a traditional neural network to read.
Finally, we pass this flattened vector into a fully connected network. Every single neuron here weighs the extracted features. Does it have a red curve? Yes. Does it have a stem? Yes. These neurons calculate everything until they reach the final output layer. Here, an operation, often called a softmax function, evaluates all that evidence and spits out a probability distribution. It tells us mathematically the exact percentage of confidence the algorithm has that the original, raw grid of pixels is, in fact, an apple. And honestly, that is the true magic of the convolutional neural network. By using channels, sweeping filters, compressing through pooling, and flattening the results into a fully connected network, we've literally taught a machine to see. It's a fascinating thought, right? We use this pipeline to find an apple today, but this exact same architecture is out there right now, detecting tumors in MRI scans, identifying distant galaxies, and powering the facial recognition in your pocket. Knowing how this assembly line works, what will you train your CNN to recognize next? Thanks so much for exploring this with us today, and keep learning.